Okay, so what I want to look at here is something called binary operations. And so first we want to define it. So let's do that. Okay, so definition. A binary operation and we're going to give it a symbol. So I'll call it star or multiplication in this case, but it doesn't have to mean multiplication the way we know it, but star. I'll refer to it as star for now. On a set S is a function that maps S cross S, so the cross product of something with itself, into S. And we'll do some examples in a minute. So another way of looking at this is for each pair AB that's in S cross S, we will denote the element and remember this is a function, so A comma B, right? This is kind of like, think of this as like f of x, where f is your function and x is the element you plug in from the first set to get this in the second set. So you're taking elements from here and plugging it into here, right? So elements from S cross S, plugging them into star, and you get an element in S. So that element will say, okay, so if I take this element from S cross S, we'll denote that that element, this thing, right? The AB comes from S cross S. When I plug it into the function star, we're going to get an element of S, and we'll denote it by A star B. Okay? So again, you take the element from S cross S, you plug it into your function right there, and then you get a new element that comes from just S, and it's this, A star B. Okay? So what does this mean? Okay, what this means is that for each, again, every single AB in S cross S, we assign an element A star B of S. Okay, so let's look at some examples here. And in this case, we'll ask which are binary operations. Now, when you define, when you mention a binary operation, you have to mention what the set S is too. Okay, so let's see how am I doing. Okay, so first example. Let's say we're looking at the set Z, and we're defining A and B are in Z, and we're defining AB, we're mapping this into A plus B. And in this case, I'm talking about regular addition, which is usual addition is the way that it's phrased. Usual addition on Z. So the question is usual addition on Z a binary operation? Okay, well, if you think about it, if I take any ordered pair from Z cross Z, so if I take this A and B pair and I add them together, that's always going to be in Z. And it works for any pair. So for each A comma B in Z cross Z, we assign an element of Z. So yeah, that is a binary operation. Okay, let's take a look at another one. So I'll ask this one, is usual multiplication on Z a binary operation? So if I take any ordered pair from Z cross Z, this is basically saying that that turns into A times B. Now for times, I guess I'll use a little x like that. A times B. So is that in Z? And for any ordered pair. And the answer is yes, right? If I multiply two integers, I get another integer, A times B. And so yes, this one is also a binary operation. Okay, let's look at this one. So let's define our set to be the positive integers, which for our purposes we'll also call the natural numbers. Okay, so that's going to be 1, 2, 3, dot, dot, dot. And so the question is usual subtraction a binary operation on Z plus? Okay, so that means that I can take any pair out of Z plus cross Z plus and subtract them, A minus B, so AB comes out of that. I do A minus B, and that's supposed to be in Z plus again. Well, that's not always going to work. And so an example, a counterexample, would be something like let A equal 4 and B equal 7, right? So then 4 comma 7 gets mapped to -3, which is not in Z plus. Okay, so not a binary operation. Let's look at some other ones here. So 4. Let's let our set be all the positive real numbers. Okay, and I'm going to take A and map it to root A. All right, that's not a binary operation because this doesn't come out of R plus cross R plus. I'm only using one element, not two, right? So this is not a binary operation. A little side note here. Let's say R plus was my main set, and I'm taking this, A comma B, from R plus cross R plus, and mapping it to root A. That is a binary operation. Even though B doesn't really do anything there, you're taking something from R plus cross R plus, that's the key, and mapping it to something in R plus. Okay. Do I have more examples? Let's take a look. Oh, I got a bunch more. All right. Let's look at R. And we'll take AB from R cross R. And I'll write it using some other notation too. Let's say that my binary operation maps that to be A plus 17B. Okay, so I take stuff from R cross R, I apply that rule to it, and this is always going to be in R. So, yes, it is a binary operation. This one, let's try this. We're looking at all real numbers. I'm going to take AB from R cross R, and I'm going to define A star B as 17. So AB always maps to 17. Well, that's also a binary operation because 17 is in R, and any AB that I take from R cross R will map to 17. So that is a binary operation. Okay. Here's one that's a little trickier. Let's look at R. So my first element comes from R cross R. And I'm going to map that to be A to the B. Okay? Now that looks like this should always be an R, but there is a counterexample. There are a couple counterexamples, right? This is not a binary operation. Because I can actually find some ABs, these ordered pairs AB, that don't map to the real numbers. Like, if A equals 0 and B equals 0, then A to the B does not exist, right? So not in R. Remember, it has to work for every ordered pair you can take from that cross product. Also, if A equaled -4 and B equaled a half, right, then A to the B would be in the complex numbers, but not in the real numbers, right? So not a binary operation. Two counterexamples there. One kind of stranger example. Let's look at this. Okay, let's say S is the set 1, 2, 3. And I'm going to explicitly define every single mapping. 1, 2 maps to 1. 1, 3 maps to 2. 2, 1 maps to 1. 1, 1 maps to 1. Let's see, what else? 2, 2 maps to 2. 3, 1 maps to 2. 3, 3 maps to 1. 2, 3 maps to 3. 3, 2 maps to 1. Now, I've actually covered every possibility that you can do for ordered pairs with these things. There are 8 possibilities. They're all there. And if you look at everything that they map to, they all map to elements of S. So I've actually gotten everything from S cross S mapping into stuff just in S. So yeah, that is a binary operation. Now, coincidentally, if I tweak this and I made this 0, right? Now it's not, because 0 is not an S. Just so you understand that idea. Let me get rid of that. And go back to this. Now there's another way of representing this that's a little more convenient, I think. So that would be to make a table. So you put your operator there. In this case, it's star. And then I'm going to put my elements of S along the side here and along the top. And I think I've hinted at this before. So when I do something like 1 star 2, what that means is take the first element from the first row and the second element from the column. Right, so 1 star 2 in this case comes from here. That equals 1. Let me use another color to match stuff here. So let's look at 1, 3. Right, so 1 star 3 equals 2. So 1 star 3, this one should be a 2. 2, 1 should go right here. That's a 1. 1, 1 is a 1. Let's see, what's next? 2, 2 is a 2. 3, 1 is a 2. 3, 3 is a 1. 2, 3 is a 3. And 3, 2 is a 1. So you can also do a check this way. You can basically just look at everything here and see, are all those elements of S? And if they are, then you're good. Okay. So another term that we need to know. Let me go back to black. Definition. A set is closed under an operation if the operation assigns to every ordered pair of elements from the set an element of the set. So that means you take every ordered pair from like S cross S and you assign to it something from S, which, if you think about it, the definition of binary operation implies that it's closed. The reason that you look at this stuff is actually for subsets. You start to look, well, is a subset closed under the same operation? Here's an example of a set that's not closed, right? So under a certain operation. So we've got, I'll do the positive and negative integers. Oh, positive and negative odd integers. Sorry, let's do that. Now, if I just did the integers, I think we had this up here, didn't we? Where is that? Yeah, the very first example we did, if I do usual addition on Z, that's a binary operation. So, and it's closed because every Z cross Z element that I can take, I assign an element from Z. So that's closed, and it's a binary operation. But if I do it with just the odds, right, this one's not closed under addition, usual addition. Eventually we'll start talking about addition differently. And an example, well, you can take any pair really, 1 plus 1, right? That's 2, but that's not an S, so it's not closed. Let's try this one. Example. So this was another example. Let's let plus and dot be the usual binary operations of addition and multiplication on Z. Okay, and we're going to let H equal all the squares where n has to come from a positive integer. Is H closed under addition? And is it closed under multiplication? Okay, well, under addition, it's not closed. And in order to prove that, you just need a counterexample. So let's pick the first two squares, right? So 1 comes from H, 4 comes from H, and so this, under addition, is the same thing as saying 1 plus 4, which equals 5, but 5 is not in H because it's not a perfect square. So there's your counterexample. If we look at the multiplication, well, it is closed. And here's the proof. Okay, so let R be in H and S be in H. So I'm picking my two elements. So then R comma S is the same thing. That comes from H cross H. Right, so that's good. We want to prove that this element gets assigned under multiplication another element in H. So that's the same thing as R times S. Right? Oh, regular times. So I'm using a dot now. Okay, well, since R is in H and S is in H, that means that there must be integers, let's go n and m, in Z plus such that R equals n squared and S equals m squared. Okay, well that means that R times S down here is the same thing as saying n squared times m squared. Well, we know from the rules of algebra that that turns into n times m all squared. And n is in Z plus, m is in Z plus, so nm is also in Z plus, because you multiply two integers together, you get another integer, positive. So let me write that here. nm is in Z plus. So that means that nm squared is going to be in H. And so we basically just showed that R times S is some integer squared. So since H is all the squares, right, up here, since H is all the squares, then we know that that's going to be closed. I take an ordered pair, I multiply them, and I end up with another element that's in H. Okay, so H is closed under multiplication. Multiplication. All right. Do I want to keep going? Well, these are obvious. Well, hopefully obvious. An operation is commutative. Whoops. Come on. Move that down. There we go. If A cross B, or A star B, equals B star A, and it's associative if A star B star C, where I pair these two, is the same thing as A star B star C. Now, these aren't always going to be true. Like, if you look at subtraction, that's not commutative, right? Because 7 minus 3 is not the same as 3 minus 7. So, okay. So, that does it for me. All right. I'll see you guys Monday. If I can figure out how to turn this thing